And we have here another problem at the screen, and it says something about magnetic lift. That is a very basic problem, and the statement of the problem is a rigid thin conducting ring lying in a non-conducting horizontal surface. Okay, in a homogeneous magnetic field B, which has horizontal magnetic lines of force. So everything is horizontal till now, and the mass of the ring is m, its radius is r, and what current in the ring will cause it to rise off the surface, So we have the picture here already embedded in the screen, this picture, and let us consider the ring as it lies horizontally, because it is given in the problem, so we don't need to have to consider it, but it's horizontal, right? This picture gives the top view of the ring. So, and we chose two small element of length delta L, H, this one and this one, both of them, and they are located obviously at points C and D, and symmetrical. Basically, they are symmetrical to the ring's diameter. Diameter is AB. You can see it here. There are two kinds of B here, but this AB are the endpoints of a diameter of the diameter of one of the diameters of the ring. So don't confuse with them. And this first element, you need to consider two parts of this delta 1, because this part is not going to get any response. Basically this component of this delta L, this component is not going to receive any response from the external magnetic field, which also lies in that direction. So IL cross B will be equal to 0 for this segment. So this segment is important. Only this component of delta L, call it delta X. It is given in this picture. And the force on this delta L due to this magnetic field is in vertically downward direction, and this force you will be able to write this force simply as delta F1, and it can be written as current I, which is not given. Basically we need to find it, this current I, so I'm writing it as I B delta L sine alpha. I don't want to put the alphas into actions, so I'm going to write down this length as simply as delta X. So that means Bi delta X. Delta X is basically the projection of delta L on the diameter AB. And the second element is, again we can think about the second element. Just it will also have two components, one in vertical direction and one in horizontal direction. And the horizontal component of delta L, I would like to call it delta X, and magnetic field is in this direction, vertically upward direction. So it will receive a force in vertically upward direction. This is the direction delta F2 here, and delta F2 will have the same magnitude, because nothing changed, only their directions are different. So we have described the forces acting on two symmetric elements of the ring, and these forces are equal in magnitude and opposite in direction, so they form a force couple, and that produces a torque relative to the axis AB. This AB, these two forces, they are bound to create a torque about the axis AB. And this torque thing, this if I get some space here, if I can, I will be able to write the values of torques created by these two forces on the small segments delta F1 and delta F2 as delta tau. And delta tau is nothing but the magnitude of delta F1 or delta F2 divided by distance between them is the total length CD. You are perhaps remembering CD is this length. So, and write the value of delta F1 as I B delta X multiplied by CD. And if I bring you this picture again, you can think that CD, the length CD multiplied by delta X, is this area, this whole area. So if you wish, you can write it as call this area as S, so it will be simply as BIS, or call it delta S because we are working with elementary elements, so call it delta S. If you are worrying why it is not DS, basically it is, I'm using the terminology here. Delta is definitely the area of the shaded region or dashed region, and you can see that if we try to find the net torque acting on the ring, we will have to consider the torques acting on every torques acting on the analogous pairs of small segments symmetrical to diameter AB. You can see from this picture again. Then we are trying to find the net torque on the ring, and there are many analogous pairs of elements like CD on the ring, and they will all produce torques about this diameter AB. And we can find that a thin conducting ring carrying a current I located in a horizontal magnetic field V will be affected by the torque as BIS, where S can be taken as the whole area of the ring. Because see the mathematical, if you don't understand, see the mathematical picture. And since we need to calculate delta T as sum of delta, all delta T is acting on similar segments like CD, then you can do nothing. B and I are constant. So we are going to add up the areas, and this is the whole area, so that we can write as BI pi r square. Remember, r is the radius of the ring. So this is the net torque acting on the ring due to magnetic forces, and this is created by force couples. And this torque tries to turn the ring around the horizontal axis AB. But now focus your attention on other things like again I'm opening the picture, and when the ring almost begins to rise, two forces are going to oppose its rotation. One is downward vertical force of gravity, of course acting at the ring center, and the upward normal applied at supporting points of the ring, you can guess. And as the ring is still in equilibrium, you can say one thing. These are the two forces acting on it, because force couples as a resultant value is 0. You can simply write in equilibrium that mg minus n is equal to 0, or you can call it n equals mg. So the mechanical forces develop a force couple of their own. N and mg are of same magnitude but opposite in direction. So these mechanical forces, they have also developed a force couple of their own, and they can produce a torque like mgr. Yeah, they're trying to rotate about the diameter, so they will produce a torque of value mgr. R is the radius of the ring, and in equilibrium the total torque of all forces, that is the sum of magnetic and mechanical torques, is equal to 0. And you would like to write torque produced by magnetic forces is equal to torque produced by mechanical forces, and we have the values of both the torques, and you are going to write down the equation that Bi pi r square is equal to mgr, and this will give you the value of current we are looking for, and this is nothing but mg by pi br. So we solved the problem. Thank you very much for watching.